Hello, welcome to another module in this massive open online course. So in this module, let us start looking at another new topic, that is entropy. So far we have looked at different properties of entropy. When is entropy maximized? Let us start looking at another concept, that is joint entropy. Okay, so we will now start looking at a new concept, which is the joint entropy. You can think of this as the joint information in two sources, or the combined information. Okay, so basically you can think of this as the we will talk more about this later. You can think of this as the combined information when you have multiple sources. Okay, for instance, let us consider what is its relevance to the specific problem that we are interested in, which is in the context of communication. Let us consider a simple communication system. Okay, so we have a channel. Okay, let us consider a simple example in which we have a channel, we have a set of transmitted symbol input symbols. So these X are your input symbols, Y are the output symbols. X can belong to the alphabet S0, S1, Sm minus 1, Y can belong to R0, R1, Rm minus 1. Okay. So now we want to see what is the, so now X is the input, Y is the output. Now we want to see what are the properties of the joint information, or what are the properties of information in X and Y. So it is now important to study properties of information in X comma Y, correct, to understand the fundamental limits of communication. Okay. Now the reason being, we have X which is X which is the input, and Y, right, which is the output of this communication channel. So we want to know how much information is communicated across this channel, what information does Y convey about X, how much information does the input X convey about Y, what is the total information in X. So these are questions which are important to answer in order to characterize fundamental, right, properties, right, fundamental aspects pertaining to communication of information over this communication channel. Okay, and so that is what we are interested in looking at, and the framework for which we will start developing in this module, first by understanding what is the notion of a joint entropy between these two, the input X and the output Y. Okay, so let us now look at. Okay, so of course we have seen that this is a alphabet of size M, alphabet of size M, and this is observe that the output and input alphabet size need not be same. So I am just going to change this to N. Okay, because the output and input alphabet can have different size in comparison to the input alphabet. Okay, now, okay, so let us now understand this. So let us now make a table for this to describe it better. I am going to make a table for this, okay, just to describe this better. Okay, and what I am going to have here are basically your so this I am going to divide into x comma y. So, various possible values, that is S m minus 1 and various possible alphabet of y, that is r 0, r 1, r n minus 1. And we look, if we look at the ijth entry, okay, and call that as Pij, okay, this corresponds to Pij, basically corresponds to x equal to Si and y equals, the output symbol y equals Rj. So, we are denoting this Pij. So, this two dimensional table we are denoting Pij by Pij, the probability x equals Si, y equals Rj. You can also think of this as the probability x equal to Si intersection y equal to Rj, that is our P, that is our probability. We are denoting this by the probability Pij. Of course, naturally we must have 0 less than equal to I less than equal to m minus 1, 0 less than equal to j less than equal to n minus 1. M is the size of the alphabet x of x from which the input symbols are drawn, and n is the size of the alphabet from which the output symbols appear or occur at the output of this communication channel. Okay. And now we want to define this notion of joint entropy for this kind of an input output scenario, x and y. Okay. Now, if you look at the total number of, so naturally, now one way to understand is, naturally one can think of x comma y as a 2D, that is, so we have looked at, so 2D source implies that you have two components x and y, that is, you have an ordered pair, correct. So, two dimensional source with symbols Si comma Rj. Okay. So, one can think of this as two dimensional symbols, and therefore, total number of such 2D symbols. Okay. So, total number of there is total possible combinations of x comma y. M can take, x can take m possible symbols, n can be y can take from n possible symbols. The total number of 2D symbols, two dimensional symbols, is m into n. And now the entropy, the joint entropy, is nothing but the entropy of this two dimensional source x comma y. Okay. The joint entropy is the entropy of this two dimensional source x comma y, and that can be defined as follows. Okay. Which is denoted by h of x comma y. So, I will have h of x comma y, let me just write it a little clearly, that is basically your h of x comma y equals, well, summation I equal to 0 m minus 1, summation j equal to 0 to n minus 1. Remember, each such 2D symbol occurs with probability Pij, that is what we have said, occurs this Si comma Rj, it occurs with probability Pij or Pij, just let me simply denote it by Pij. So, this is Pij log to the base 2 1 over Pij. So, this is the joint entropy. Okay, this is termed as the, that is, you look at x comma y as a 2-dimensional source, look at the probabilities of intersection, that is probability that x is equal to Si, y is equal to Rj, there are a total of mn 2-dimensional symbols. Now treat this as a 2-dimensional source and compute the entropy of the 2-dimensional source, that is summation over all the symbols of this 2-dimensional source, probability times log to the base 2 log 1 over probability to the base 2. Alright, we are now extending. So, as a matter of fact, we are now extending the definition, the same definition that we had for a simple source before, to this new source that we are calling as that we are terming as a 2-dimensional source. Okay, and this metric which characterizes the joint information, the total, you can think of this is termed as the joint entropy, and you can think of this as the information per symbol in x and y together, that is, if you look at x and y together, that is information conveyed by x and y together. That is the meaning of the word joint, x comma y together, or basically jointly. Okay, so that is basic meaning of this term joint entropy. Okay, so let us look at an example to understand this better. Consider the example below. Let us look at a simple example to understand this concept of joint entropy. Okay. Okay. So, I have here again x, y, R0, R1, R2, R3, okay, and y S0, S1, S2, S3, and the various probabilities are 1 over 8, that is the probability that of x equal to S0, y equal to R0, 1 by 16, 1 by 32, 1 by 32, 1 by 16, 1 by 8, 1 by 32, 1 by 32, 1 by 16, 1 by 16, 1 by 16, okay, and finally you have this. Okay, for instance, if you take a look at this 1 by 32, this is equal to the probability that well, x is equal to S1 comma y is equal to R2. Okay, that is what we have said. This is basically your P1 comma 2. Okay, because Pij is the probability that x equal to Si, y is equal to Rj. So, this is your Pij. Okay. And now, so the total number of 2D symbols, of course, now you can see, because each has 4 symbols, S0, S1, S2, S3 and R0, R1, R2, R3. Total number of 2D symbols this is 4 into 4 equal to 16. Alright, you taking all the possible combinations of the symbols for x and symbols for I, you have total possible 2D symbols, okay, Si comma Rj. Okay. And now just to make a check, of course, we know that the total probability must be equal to 1. So, we must have, and you can check this to just see if it is a valid distribution, to check if the probabilities or probability or the two dimensional probability mass function, we must have summation I equal to 0 to m minus 1, summation j equal to 0 to n minus 1 equals, this must be equal to 1, and we know this from our total probability. Okay, sum of the probabilities of all the events okay, sum of the probability. So, this is right, this is mutually exclusive and exhaustive. Okay. So, the total probability must be add up to 1. So, let us just quickly check it, check if the total probability is adding up to 1, alright, although that must be the case, but just helps us to additionally check and confirm it. Okay. So, that would be, so we have total probability the total probability where there is one symbol with probability 1 by 4. So, 1 by 4 plus 2 symbols with probability 1 by 8, 1 by 8 plus 6 symbols with probability 1 by 16, 6 into 1 by 16 plus 4 symbols with probability 1 by 32, 4 into 1 by 32, that is 1 by 4 plus 1 by 4 plus 3 by 8 plus 1 by 8, and you can check this is equal to 1. So, this is basically a valid probability, which implies you have a valid probability distribution. Now, from the total now another interesting thing is also from the total probability rule. We have summation I equal to 0 to m minus 1 probability Si comma Rj must be equal to probability of Rj, that is corresponding to an Rj, symbol Rj. If you sum over all the SIs, probabilities corresponding to each SI, correct, you will get the net probability corresponding to Rj. This is from the total probability rule, because remember these SIs S0, S1, Sm minus 1, these are mutually exhaustive, these are mutually exclusive and exhaustive. Okay. That is, the intersection of each of these symbols is phi, and their union spans the entire set. All right. And therefore, if you look at probability Si comma Rj, this is nothing but the probability Si intersection with Rj, and from total probability we have basically probability A naught intersection B plus probability A1 intersection B plus so on up to probability AM minus 1 intersection B is 1. If, of course, this you should know from the theory and probability random variables, but anyway, just to refresh your memory, this is if A naught or if AI intersection Aj equal to phi for all I comma j, that is implies A naught A1 comma A m minus 1 are mutually exclusive and they are exhaustive, that is A naught union A1 union A m minus 1 equals S, that is the sample space. So, these events are basically a partition of the sample space. Okay. So, each of these events is disjoint, that is their intersection is phi, correct, and their union spans the entire sample space. For instance, what we have here in terms of the symbols, these symbols S0, S1, Sm minus 1, these are disjoint, okay, in the sense that occurrence of one precludes occurrence of other, and they are exhaustive in the sense that the symbols must belong to one of these, S0, S1, Sm minus 1. Okay. So, therefore, we must have probability, that is, therefore, if you sum over the probability for each Rj, if you sum over the probabilities, probability Si comma Rj corresponding to each Si corresponding to all Si, you get the probability Rj. Naturally, also if you sum over the probabilities of all Rj corresponding to an Si, you get the probability over Si. Okay. This is again according to your total probability rule. Therefore, what this means is basically if you sum over each column, that is R0 for instance, R0, R1, R2, these represent each column. So, if you sum over each column, you get the probability, that is sum over the probabilities for each Ri corresponding to all the Ss, you will get the probability total probability corresponding to that Ri. Similarly, if you sum across the rows, that is sum over all Rj corresponding to each Si, then you will get the probability of that Si. Okay. So, therefore, we have probability of R0 equals, so let me illustrate this thing, R0 equals 1 by 8 plus 1 by 16 plus 1 by 16 plus 1 by 4. So, that will be 1 by 8 plus 1 by 16 plus 1 by 16 plus 1 by 4. So, that will be 1 by 8 1 by 1 by 4. So, that will be half. So, probability of R naught equals half, probability of R1, I am just writing it over the column, probability of R1 equals 1 by 4, probability of R2 equals 1 by 8, probability of R3 is also 1 by 8, and probability of S naught, you can check, probability of each S naught is 1 by 4, that is all these Ss are equiprobable. Okay. So, all are equiprobable. Okay. And therefore, now what you will have is, let us proceed to compute the joint entropy. The joint entropy, now as we have seen, joint entropy x comma y remember this is h of x comma y summation over I summation over j p I j log to the base 2 1 over p I j. So, this is equal to, well, there are two symbols with probability 1 over 8. So, twice 1 over 8 log to the base 2 8 plus there are 6 symbols with probability 1 over 16, 6 into 1 over 16 log to the base 2 1 over 16, that is 116 plus that is log 16 to the base 2 1 over 4 log 4 to the base 2, only one symbol with probability 1 over 4, and in fact there are 4 symbols with probability 1 over 32, 4 over 32 log 2 to the base 32, and you can see this will be basically, you can see this will give you, well, this will give you 3 over 4 plus, so this will be 16, 4 divided 1 over 4, so this will be 3 over 2 plus half plus 5 over 8, that is, if you look at this, this will be over 8, you have 6 plus 12 plus 4 plus 5, that is basically you have for 10, 22 plus 5, that is 27 over 8, which is equal to 3.375 bits. So, we have the joint information, the joint entropy h of x comma y for this example equals which we have computed treating the symbols as 2D symbols. Okay. So, basically what we have done now is we have computed the joint entropy of x and y, which is denoted by h of x comma y. So, in this module basically we motivated this problem of joint entropy as considering a simple example of a communication system in which you are transmitting symbols x, receiving symbols y. So, you would like to understand the interplay, better understand the interplay of the information, various aspects of the information between corresponding to these two quantities, that is the input x and the output y. Okay. We have defined this notion of joint entropy and we have seen a simple example and computed the joint entropy. We will further explore the properties of joint entropy and their relevance in the context of communication in the subsequent modules.